Let me start by quickly running through what we discussed last time. We started with the subject of the postulates of quantum mechanics, and we introduced the first and second postulates of quantum mechanics. The first postulate basically tells you that the state of any quantum system at any time t is defined by specifying a vector which belongs in the Hilbert space of the physical system under investigation. Okay, so once you know what this state vector psi is, you can figure out everything else you need to know about the system. But everything else you need to know about the system is not set in a deterministic fashion as we do in classical mechanics, but instead it is formulated in a probabilistic fashion, and how the rules of probability are used in quantum mechanics would be the subject of the next few postulates. So the second postulate of quantum mechanics is basically telling you that every observable in classical mechanics is described by a corresponding operator in quantum mechanics. Okay, so with these two postulates, we should now build the theory of quantum mechanics by introducing the other three postulates. And today we will talk about the third postulate exclusively. Okay, this is a very important postulate, and we have to understand the physical meaning of this postulate completely. So now that we have told you that every observable in classical mechanics, like energy or angular momentum, has a corresponding operator in quantum mechanics, the next logical question is, what does this operator do? So we have two ingredients in quantum mechanics in place now. One is the notion of the state vector that describes the dynamics, supposedly, of the system. And second is the idea of operators that act on the vectors in this Hilbert space of the quantum mechanical system. So what do we do with this? In comes a third postulate of quantum mechanics, which in some sense is the most counterintuitive of all postulates in quantum mechanics in more ways than one. So the third postulate of quantum mechanics is as follows. It tells you a rather remarkable thing. It tells you that the only possible results of the measurement of a physical observable like energy, angular momentum, whatever it is, momentum, let us call this observable A, classical observable A, is one of the eigenvalues of the corresponding operator in quantum mechanics, which is A hat. This is a remarkable statement. It tells you, without actually doing the experiment to measure the position or the angular momentum or the spin of an electron or whatever it is, it tells you that the only thing that you can possibly get upon measuring this is one of the eigenvalues of the operator. So before you actually do the experiment, you are putting in certain restrictions on what kinds of answers that you can possibly get. Okay, there is no analog in classical mechanics for this statement. Classical mechanics never tells you, before you, for example, measure the energy of a spinning top, classical mechanics does not tell you that the answer to this has to be either +3 or -4.5. Okay, it tells you that, well, go ahead and measure it. It must be a measure of how fast the top is spinning, right? It can take any value. I do not know what value it can possibly take unless I actually measure it. Now, quantum mechanics tells you something rather intriguing. It tells you that, no, I cannot tell you exactly what you will get without you actually measuring it. But I can tell you something. I can tell you that these are the possible values that you will get. You will get one of these possible values. Okay. Again, how can this be is a very different question, which is a difficult question that I will not get into. But we will, in this lecture, explore the consequences of this statement. Again, to explore the consequences of the statement, let us take a very simple example in 2 dimensions. 2-dimensional linear vector spaces is a very, very simple example in which I can illustrate many of these seemingly difficult statements. Okay. So first of all, absorb this statement. It tells you that before you measure something, the only possible results of measurement are the eigenvalues, one of the eigenvalues of the corresponding operator. Now, there is 2 kinds of spectra that you can get in classical mechanics. For example, the spectrum of position or momentum or angular momentum, and not angular momentum, spin angular momentum, orbital angular momentum. There are continuous spectra and there are discrete spectra. A continuous spectrum simply means there is an infinite possible number of eigenvalues for the corresponding operator. So this is not showing up, I think. So let me stop share and share it again. This is a recurring problem that I have. Okay. Now, if I'm talking about something like position, the position of a particle is, I will talk about function spaces. When I talk about function spaces, this statement should be clearer. The position operator can take any eigenvalue. There's an infinite number of eigenvalues it can take. Okay. It is what an example of a continuous spectrum. Now, in the case of a continuous spectrum, this statement doesn't really bother us that much, right? For example, if I have an infinite number of values, then basically quantum mechanics is telling me that, okay, I should pick from this infinite number of values. But the statement is also true if you only have a finite number of values. For example, if you live in a 2-dimensional, so I'll illustrate this using a very simple example, illustration. Okay. So let us marry the first, second, and third postulates together with this illustration. So consider a 2-dimensional linear vector space. Okay. Now let us say that this linear vector space is spanned by the kits 1 and 2. Okay, spanned by the kits spanning the space. Spanning the space is simply meaning that I'm talking about the basis vectors, which means these are the basis kits in that state. Now, suppose if I write down a Hamiltonian operator in this linear vector space, H. Okay, I can write it any which way I want. And let me write a corresponding 2 by 2 matrix form for this. Okay, let us say that this is something H11, H12, H21, H22. Okay, all right. So I have written down an operator. This is an operator that measures energy. Okay, so as we discussed in the last class, energy is measured by what is called the Hamiltonian operator H. So I've written down a Hamiltonian operator H in this 2-dimensional linear vector space. Okay, all right. So let me say that there is 2 eigenvalues for this operator, for this matrix. Eigenvalue E1, eigenvalue E2. Okay, this corresponds to an eigenvector U1 and this corresponds to an eigenvector U2. Okay. Now this Hamiltonian operator is a Hermitian operator. Remember that every observable in classical mechanics is replaced by a corresponding Hermitian operator in quantum mechanics. The Hermitian word is very important. Now you realize why the Hermitian word is very important, because we have introduced a third postulate. The third postulate tells you that the results of possible experiment can only be one of the eigenvalues, which means the eigenvalues better be real. If I'm measuring energy, I cannot claim that the energy of this system is 3 + 2 I joules. That doesn't make any sense, right? The energy eigenvalue has to be real. So the operators I choose have to have real eigenvalues, and Hermitian operators are the candidate operators that have real eigenvalues. They're guaranteed to have real eigenvalues, okay? So let me choose this Hamiltonian operator, which I've written down in this 2-dimensional linear vector space, which has 2 energy eigenvalues because it's a 2 by 2 matrix. Let us assume that these 2 eigenvalues are non-degenerate. Okay, assume the spectrum is non-degenerate. I'll talk about what happens if there is degeneracy in the problem. Non-degenerate simply means that the energy eigenvalues are not the same. E1 and E2 are two different energy eigenvalues. Okay. All right. So now let us try to understand many of the statements that we have talked about in this particular example. So the first postulate tells me that, let us say that this is the, we are talking about some quantum system, and this quantum system is described by a state vector psi. The quantum system under investigation, whatever it is described by a state vector psi in this two-dimensional linear vector space. Okay. All right. So I want to know what the energy of the system is. This is my question. This is a perfectly reasonable question to ask in classical mechanics. I'm trying to ask, what is the energy of the system? Okay, this is the question that I want to ask. So quantum mechanics gives you an answer, but in a rather different sense. So let me try to tell you in what sense quantum mechanics answers this question and what are the possible things that you can extract from this question. The first mathematical statement that we can make is the following. Since this state vector psi is in a two-dimensional linear vector space, I can write this state vector psi as, let us say, something times the base kit 1 plus something times the base kit 2, because 1 and 2 are the basis vectors of the system. But here we will use the first mathematical fact. What is the first mathematical fact? Hermitian operators give us a complete set of eigenkits, right? Hermitian operators give us an orthonormal or give us a complete set of kits or vectors, which means that I can use the basis kits of the Hermitian operator as, I can use the eigenkits of the Hermitian operator as basis kits. So instead of working in the space 1 and 2, I might as well work in the space U1, U2. Okay, this you hopefully by now agree and understand. So if I can expand this state vector as a linear combination of the basis vectors, I can expand the state vector as a linear combination in the 1, 2 basis kit, or I can equally well expand this as a linear combination of the U1, U2 basis kits, right? That is also something that I can reasonably do, because U1 and U2 also give me the eigenkits of the basis kits of the two-dimensional vector space under investigation. The question is, why do I want to do that? Okay, why should I do that? What does it help me with? Well, remember the question that I'm asking. The question that I'm asking is, what are the possible energies of the system? Well, this is a very simple question to answer. The possible energies of the system are one of the eigenvalues of the system. So I know before I do any experiment that the energy of the quantum mechanical system that I'm investigating can only have two values. It can either have E1 or E2, because these are the two eigenvalues of the Hamiltonian operator for this particular system, right? But before I do the experiment, I cannot definitely say that if it'll be E1 or if it'll be E2. But what can I say? Well, I know that I can get either E1 or E2, which also means that there is some possibility that I can get E1. There is some possibility that I can get E2. 2. So the question is, what is the probability that I will get E1 or E2 upon measurement of energy? I want to answer this question. Before I answer this question, are there any questions about whatever I've done thus far? Any questions or any comments? I've used the first postulate and second postulate because I've used the first postulate because I've blindly told you that the quantum system is described by some state vector psi. Okay. Then I've used the mathematical fact that I can expand this state vector as a linear combination of the basis kits. And I can use the basis kits as is it 1 or 2, or I can use the eigenkits of the Hamiltonian as the basis kits and write down equation number 2. Okay. Now I've used postulate number 2 because I know that the energy measurement can give me only 2 values for this particular system. Of course, if I'm living in a 5-dimensional linear vector space and I have a 5 by 5 matrix as the Hamiltonian, I can have 5 different possible energies of the Hamiltonian. If I live in an infinite dimensional vector space, my Hamiltonian operator is infinite dimensional, then there is infinite number of values. But for this particular system, there is only 2 possible results of measurement. Okay, so somebody is asking me, I don't understand how the state can be expanded as eigenvectors of the energy operator. So remember that aside, so remember some basic facts about Hermitian operators. Hermitian operators have real eigenvalues and the eigenvectors of a Hermitian operator are orthogonal to each other. Okay, so the second statement means that if the Hermitian operator, for example, is a 3 by 3 matrix, it has 3 eigenvectors, u1, u2, u3. Then this means that u1, u2 equals u1, u3 equals u2, u3 equals 0. Okay. Now you can go ahead and normalize the eigenvectors. The eigenvectors are not guaranteed to be normalized, but you can normalize the eigenvectors such that ui is 1. Okay. How would they correspond to the same state which was expanded in terms of kits 1 and 2? Okay, I'll answer this question. Now we can go ahead and normalize these vectors, which means that combining these two statements, I can write ui, uj. The overlap of 2 of these eigenkits is delta ij. Okay, which means they're orthonormal to each other, which means ui are a good set of basis kits. Okay. Now again, remember that we talked about vectors. Suppose if you think of a Cartesian coordinate system and you think of a vector in Cartesian coordinate system, I can expand this vector in terms of I, j, and k, the basis vectors of the system. But there is nothing that prevents me from choosing another set of basis kits, which is some linear combination of I, j, and k, such that, so I can describe in Cartesian coordinate system, in Cartesian coordinates, I can write, let us stick to 2 dimensions for this time being. I can write this as, let us say, a1 prime I cap plus a2 prime j cap. Okay. This is my, I can think of this vector as this guy, right? Oops. So this is my I cap direction, this is my j cap direction. and this vector has x component a1 prime and y component a2 prime. So this means that I am working in the ij basis. But remember that we worked out an example where we claim that there is no reason to stick to the ij basis. I can write an I plus a new basis, which is something like this. Okay, call this E1, E2. And in this E1, E2 basis, I can write my A vector as some A1, E1 plus A2, E2. Okay. Now remember that the coefficient of these two basis kits, A1 and A2, will not be the same as A1 prime and A2 prime, but it is the same vector, right? A vector is a vector is a vector. Nothing happens to the vector, but the way you describe the vector depending on the basis kits, the components of the vector might change. In the ij basis, this vector can be written as a column vector A1 prime, A2 prime. In the E1, E2 basis, this vector can be written as a column vector A1, A2. Okay. Similarly, in this two-dimensional vector space, my state kit can be expanded as a linear combination of the basis kits. Instead of 1 and 2, think of ij. In terms of ij, that is equation 1. But I can write down any Hermitian operator and write down its eigenkits in this two-dimensional vector space. And I can use these two eigenkits of the Hermitian operator as the basis kits. Okay, so I'm basically doing a basis transformation. But the state vector is a state vector is a state vector. The state vector hasn't changed. But if I express the same state vector in terms of a new set of bases, its coefficients will change. That's why the coefficients of the psi in equation 2 are not the same coefficients as in equation 1. For exactly the same reason that the coefficients of A vector are different in the ij basis and E1, E2 basis. That is all I'm saying. Is this clear? Are there any questions about this before we move on? Because this is important to understand. Okay. So now let me move on. So the question, so I have expanded my psi as a linear combination of the eigenkits of the energy operator. A1 U1 plus A2 U2. The reason I'm doing this is because I'm asking a question about what are the possible results of experiments. Well, upon measurement, I can get E1 and E2. So I want to compute the probability of getting E1 or E2. Okay. Now, a little bit of vector analysis should make this answer to this question rather clear to you. Remember that if I act this state vector on by H operator acting on this is equal to H operator acting on A1 U1 plus H operator acting on A2 U2, which is the same as A1 H1 acting on U1, but U1 and U2 are the eigenstates with energy eigenvalues E1 and E2. E1 U1 plus A2 E2 U2. Okay. Sorry, the left hand side should be H acting on psi. Okay. Now it's clear from this that I can get the value E1 or E2. But what is the probability of finding E1? The probability of finding E1 is what is the overlap of this state with the vector U1. The probability of finding E2 should be proportional to the overlap of this state psi with the vector U2. Okay. So writing this state vector psi as A1 U1 plus A2 U2 is very helpful to answer this question because I can easily calculate the overlap of this state along the u1 direction or along the u2 direction. Okay, so if I calculate the overlap of this state along the u1 direction, u1 psi is basically a1 u1 u1 plus a2 u1 u2. But since u1 and u2 are orthonormal eigenstates, u1 u2 overlap is 0 and u1 u1 is 1. So this is nothing but a1. Okay. So this is called the probability amplitude. This is the probability amplitude. But the probability of measurement of E1 is given by the absolute square of the probability amplitude. This can also be written as the absolute value of the overlap of U1 psi, the whole square. This is a very important property. So what does this tell me? This tells me that before I do the experiment in this two-dimensional linear vector space, before I actually measure the energy, there is two possible energy eigenvalues that I can possibly measure. Suppose if I hook up my apparatus and measure the energy of the quantum system, I know that I will get E1 and E2. But before I do the experiment, I do not know that I will get E1 or I will get E2. Before doing the experiment, I can only make a probabilistic statement as to what is the probability that I can get E1 and what is the probability that I can get E2. Okay, this is a very probabilistic theory in that sense. The probability that I can measure E1 is given by the overlap of the state of the system with the eigenvector corresponding to the energy eigenvalue E1. The probability similarly that I can get E2 would be A2 square, which is the absolute square of the probability, square of the overlap of the state with the eigenvector corresponding to the eigenvalue E2. Okay, so this is nothing but very simple statement. See, suppose if I take this A vector, which is A1 prime I plus A2 prime J, then I am asking the question, how much of the A vector is along the X direction? How much of A vector is along the Y direction? You would say it's A1 prime is along the X direction, A2 prime is along the Y direction. The way you're computing this is basically you're taking the dot product of A with I vector and you're getting A1 prime. You're taking the overlap of A with J hat and you're getting A2 prime. That's exactly what I am calculating here. I'm calculating the overlap of the state vector with the eigenvectors of the operator in question. Suppose if I, instead of energy, suppose if I want to measure the spin, then I would take the spin operator and calculate its eigenvalues and eigenvectors, and I would say that the possible eigenvalues are this and this. Now, I will write the state vector as a linear combination of the eigenvectors of the spin operator. Okay, and then I should go ahead and do the exact same calculation. So what is the probability that I will get spin up and what is the probability that I will get spin down? That will be the absolute square of the overlap of the state vector of the system with the two eigenvectors of the spin operator. Okay, now you should remember the difference between the probability amplitude and the probability. The coefficients A1, A2 in general are complex quantities. And to get a probability out of them, to get an absolute number out of them, you have to take the absolute square. Okay. The total probability, of course, you have to get either E1 or E2 in this two-dimensional space. There is no other possibility. So the total probability has to be equal to 1, which means that A1 square plus A2 square has to be equal to 1. Okay. How is this guaranteed? Well, this is guaranteed by working with normalized state vectors. So remember that I'm taking my state vector psi as A1 U1 plus A2 U2. Okay. Again, sorry, this I have to stop share and share again. My iPad is the latest generation. My MacBook is a little old, so they refuse to talk to each other because of a generation gap. just like it happens with people. Okay. So this statement that the total probability is 1 is the same statement that the state vector is normalized, psi equal to 1. So normalized psi. Okay, why? What is psi? Psi overlap of psi with itself is given by a1 star bra u1 plus a2 star bra u2 multiplying a1 u1 plus a2 u2, which is nothing but the first term is a1 mod a1 squared u1 u1, which is 1. The second term is a1 star a2 u1 u2, but the overlap of u1 u2 is 0. Similarly, the overlap of u2 u1 is also 0. So this is equal to a2 squared plus a2 squared. And this is equal to 1 is the same statement that the state vector is normalized. So this is why in quantum mechanics it is always useful to first normalize your state vectors. In your DSC, you would have talked about normalizing the wave function. It is exactly similar. So it's useful to work with normalized state vectors, because if you work with normalized state vectors, the sum of your probabilities is always equal to 1 and you will not get any nonsensical probabilities at the end. Okay. So this was also a question that was asked a few lectures ago. Why should I normalize the wave functions? Hopefully the answer to this question is clear at this point. So let me write down the general statements in any finite dimensional linear vector space that corresponds to this. Okay, so I'm still sticking with the discrete spectrum. We'll talk about continuous spectrums next week. So suppose if you are interested in the measurement of some operator A, okay, so suppose you are interested the measurement of A, some observable A. Okay, in quantum mechanics, there is a corresponding operator. There is a corresponding Hermitian operator A hat, right? So the first step is to figure out the state vector of the system. Okay, that you have to figure out on your own by solving what is called the Schrodinger equation. We will come to that later. So let us say that you have the state vector of the system psi. Okay. Now find out the eigenvalues and eigenvectors of A. Okay, that is the second step. So you will solve the equation A un equals A n un. Okay, so these are the eigenkets or eigenvectors, and these are the eigenvalues. So quantum mechanics tells you that the possible results of measurement of A would be one of these ANs. So it would be A1, A2, A3, whatever it is. These are the eigenvalues. So you have to understand, before you do the experiment, excuse me, what are the possible results of the experiment and what are the corresponding probabilities? This is the question that you can answer before you do the experiment. What are the possible results and what are the corresponding probabilities? Okay, this is the central question that we are asking in this lecture. Remember, before you do the experiment part is very important. We will talk about what happens after you do the experiment in the next lecture. So before you do the experiment, the only things that you can claim, in fact, there's a lot of things you can claim. The things you can claim are that these are the possible results of the experiment. I don't have to do the experiment. I know that this is what you would get if you actually did the experiment. I won't be able to tell you that this is exactly, this one particular value is exactly what you would get, but I can tell you that you will get one of these many eigenvalues as the result of your experimentation. You can also say what is the probability that you will get this particular value. The way you compute the probability is by writing the state vector psi as a linear combination of the basis kits. So you will write this as alpha 1 u1 plus alpha 2 u2 plus blah blah blah. Okay. In other words, you will write this as alpha n un. Okay. And the probability that you will get some particular value, let us say am, is given by the absolute square of the overlap of that particular eigenvector corresponding to the eigenvalue un, the absolute value of that square. Okay, this is the three-step process. The question that you can ask before the experimentation in quantum mechanics is, what are the possible results of the experiments? And the other question that you can ask is, what are the corresponding probabilities? Okay, the probability of measurement is given by the overlap of the absolute square of the overlap of the state vector with the eigenvector corresponding to that particular eigenvalue. Okay. So let's clear up one possible conceptual problem in this way of looking at things. What do I mean by probability? So remember, when you throw a dice, this is the typical way probability is introduced in undergraduate or graduate, whatever it is, mathematics, right? So you say that you throw a dice and you get heads or tails. What are the chances of getting head? You get 50% chance of getting head, 50% chance of getting tail. Under what condition is this probability theory valid? It is valid under the condition that the number of throws is larger and larger and larger, right? For example, if I did, let us say 6 throws, then I am not guaranteed that I will get 3 heads and 3 tails, right? So this is something that is very important to understand in probability. But if I do 25 million throws, it is clear that 50% of my throws, well, nobody has the patience to do it, but it is clear that 50% of my throws will be heads and 50% of my throws will be tails, at least something very, very, very close to it. It might not be true if I only throw the coin, toss the coin like 5 or 6 or 7 or 8 or even 10 times. Even if you do it 10 times, you're not guaranteed that you will get only 5 heads and 5 tails. You would have to do the same experiment, the tossing, many, many, many times, right? So now what does this probability mean in quantum mechanics? Now, I am not claiming that the experimentalist should go ahead and measure the energy of the system 25 million times in her lab, right? For a simple reason that she will kill me if I ask her to do that. It's a laborious task. So we do not mean by probability in this idealized sense of looking at things probabilistically, we don't mean that I am repeating the same experiments 15,000 times. In fact, that is absolutely not the way in which you should understand this, for a reason that will be clear after I talk about what happens after you do the experiment in the next lecture. What I mean is a rather fictionalized set of experiments. What I mean is the following. Suppose if the system is given to me in a small box, okay, this is the quantum system, and I want to measure the energy of the system. And I'm claiming as a theorist that before I do the experiment, I will get energies 25 joules and 37 joules. These are the only possible results. And I will get, there's a 37% chance that you will get the first value, and there is a 37 minus 100 minus 37 is 63% chance probability that you will get the second eigenvalue. Okay, I've made this grandiose statement. But what does this mean? This means that the picture that the theorist has in his mind when he makes a statement is the following. Instead of taking one of the boxes and doing the energy measurement once, I have a sort of a fictionalized version of this experiment in my mind in which I am duplicating the system. 25 million, 100 million, whatever. Since it is happening in my head, I can choose n to be as large as possible without any worry about how much money I will spend doing this experiment, right? So I will duplicate this exact same system 25 million times. And I will contact 25 million hypothetical people and ask them all to measure the energy of the system at the same time. Okay. This is the sense in which I should understand the probability. I duplicate the system, okay, and then I measure the energy of the system exactly at the same time for all the technical lingo that is adopted is identically prepared systems, which means I should not make the system described by a state vector psi1 in my first box and psi2 in my second box. Then I'm losing the essential point of duplication. Duplication means I'm preparing an exact replica of the system. If this box is described by a state vector psi1, then I'm duplicating this box. The second box is also described by a state vector psi1. Don't ask me how I'm going to do it. Okay, this is a Gedanken way of thinking about things. This is a very, it's a fictionalized version of it's a thought experiment, but it is a valid experiment. In your statistical mechanics course next time, you will understand the relation with, you'll understand something called the ergodic hypothesis. It is intimately connected with this version that I'm describing. So I am duplicating the system a million, billion, zillion times, and I'm measuring the energy eigenvalue of the system, all these identically prepared systems at the exact same time. Then if I do this experiment, I can claim with absolute certainty that quantum mechanics is a probabilistic theory, which is a rather ironical statement. It means that 37% of these people will give me energy eigenvalue E1, and 63% of the people will give me energy eigenvalue E2. Okay, this is the sense in which you should understand the notion of probability in quantum mechanics. It does not mean that I'm preparing the state once and I'm measuring the energy eigenvalue 15 million times. No, that is not what I'm doing. In fact, I should not be doing that to answer this question. I should prepare the system once and then I should duplicate it 15 million times, and I should measure the same observable 15 million on these 15 million identically prepared systems at the exact same time. And then the laws that I've described will work very well for you. Okay. This is the content of the third postulate, but there is a little more to the third postulate, which some books will call the fourth postulate. So I'll also follow the nomenclature. The fourth postulate has to do with what happens after you do the measurement. So what happens before I do the measurement is a highly probabilistic statement. Before I do, so this is the root cause of all these famous arguments in quantum mechanics, right? So when Einstein asked, is the moon there if I'm not looking at it? Strictly speaking, quantum mechanically, you should only talk about probabilities. So I can only talk about the probability of measuring the eigenvalue E1 or probability of measuring eigenvalue E2. Before I do the experiment, I cannot tell you with certainty what I will get. Okay, this is in opposition with classical mechanics, because once I solve Newton's laws of equation, Newton's laws of motion, and I solve for the trajectory of the particle, I can tell you precisely exactly what the position of the particle would be 10 million years from now. Okay, even before I actually measure it. But that is not what quantum mechanics tells you. Quantum mechanics tells you that before you do the experiment, you can only express the results in a probabilistic way. But of course, after you do the experiments, things change. And we will talk about that in the next lecture. But I hope that this part of the third postulate is clear to you. So at a practical level, you should be able to figure out first the eigenvalues and eigenvectors of any given operator in a linear vector space. You should be able to express the state vector of the system as a linear combination of these eigenvectors to figure out the probabilities of measurement of any one of the eigenvalues of the operator before you do the experiment. Okay. So we'll stop here for today, and then we will continue on Wednesday on what happens after you do the experiment, and then we will move on to the last postulate, which is the statement of how the state vector of the system evolves as the system as time progresses, the dynamical equation called the Schrodinger equation. Okay, so we'll stop here for today, and please ask me if you have any questions at this point.